Once again, welcome to Physics STPM. Let's go to the topic. This topic is static, chapter 7. The notes can be found in this book. Okay, what are we required to study in this topic? Center of gravity, which will represent a CG or a dark point there. Center of gravity, equivalent of particles. I mean forces acting at a point there. And equivalent of rigid bodies. Okay, so these are the three topics we'll be interested in this chapter, chapter 7. Static, in dynamic. Chapter 3, we look at forces causing motion and calculating resultant force. In static, we look at Newton's first law of motion to look at forces in equilibrium. Newton's first law of motion, an object at rest will remain at rest. If it's at rest, doesn't move. Object in motion continues with the same speed in the same direction. That means it is moving with constant velocity in a straight line, unless acted upon by an unbalanced force. Unbalanced force is a resultant force. There can be many forces acting, but it will move in the direction of the resultant force. If there's a resultant force, object will move in the direction of resultant force. But in this topic, we're not interested in resultant force. Page 112 in the reference book. So in static, we are not interested. We are interested in resultant force is 0. Can the object be moving? Yes. As this one say. No unbalanced force. It can be with constant velocity. That means constant speed in a straight line. Object can be stationary or moving with constant velocity. Seamless coverage. Define center of gravity. State the condition in which the center of mass is the center of gravity. And 7.2, equivalent of particles. State the condition for the equilibrium of a particle. Solve problem involving forces in equilibrium at a point. 7.3, equilibrium of rigid bodies. Define torque as a definition. State the condition for equilibrium of a rigid body. Sketch and label forces which act on a particle and a rigid body. Use the center of forces to represent forces in equilibrium. Use triangle of forces to represent forces in equilibrium. Solve problem involving forces in equilibrium. First thing, 7.1, center of gravity. Memory work. Center of gravity, we can represent it with C or G of a body is the point. Is a point. Is the point where the weight of the body is considered to act. That means the whole weight of the body act at this point, called the center of gravity. For meter rule, it's the center of the ruler. For a uniform sphere, it's the center of the sphere. For a rectangular plate, the point of intersection of diagonal. If there's a plate there, uniform plate, you draw the diagonal, and then where it intersect, there's our center of gravity, C or G. And that's where our weight is considered to act. Center of mass of an object is the point at which an applied force produces acceleration but no rotation. Key is applied force. The force applied to the center of mass, it will cause acceleration only, no rotation. It's the same point as the center of gravity. in a uniform gravitational field. I mean, on Earth, around you, any object that you use, center of mass and center of gravity are the same point. Right? You can calculate for discrete particle, y-axis, x-axis. Right? Body is made out of many particles. Right? We look at P, the coordinate is x1, y1. Look at Q, coordinate x2, y2. Right? If you look at other particles and then look at the nth particle, the last particle, right, is xn, yn. Right? That's our axis. You want a reference to these two axes, x and y. So we can use this formula, sum of the product, right? That mass times x1, that mass times x2, and then every mass times the distance away, and then the mass of n times xn divided by total mass. Let's add all the particles, the mass of all the particles together. So that is the center of gravity, that distance from the y-axis. Same, if you want from the x-axis, we just replace the x with the y, that's all. That means the mass times the distance, mass times the distance. Same, the nth particle, mass times the distance, y, and divided by total mass. Right? This is the total mass. Right? Center of gravity for different objects, we can see it is given there. For the disk, center of the disk, ring, the same thing. Center of the disk or center of the ring. Cube is a diagonal intersect. There's a G. Dumbbell is here. Hollow cylinder is here. Square with center removed, same thing. Same as a solid square. This one show you the center of gravity can change. Stretching or bending. Is stretching or bending changes the position of center of gravity of the body. If you have a meter rule, we put a pin through the hole there, which we call a pivot, because it can swing about, and they cannot move forward because the pin is a pivot. C is the center of gravity, center of the meter rule. That's where the weight will act. Then at the pin there will be your normal reaction, pulling it outwards there. And then joining the pivot and the center of gravity, or right, you reproduce this one backwards or reproduce the weight outwards there, is called a line of action of forces. Meter rule is in equilibrium. That means it's stationary, it won't move, it won't swing. Right? There's no moment. We'll introduce this later on. There's no perpendicular distance. Line of action of N and W, they coincide. Center of gravity is on the line of action. Right? There's the center of gravity, that's a line of action. And it's below, center of gravity is below the pivot. So W equals to weight. W equals to N, normal reaction. So it doesn't accelerate, it remains stationary. Ask yourself, 3 weights are fixed along the uniform rod, which has a weight of 5 Newton and a length of 0.8 meter, as shown in the figure. Where's the center of gravity? Right? These are the different ways. Right? It didn't tell you where is your reference point. It's up to us to choose. We can choose our reference point as here, the origin as here, and then remember the weight. Right? The weight of the uniform rod act at the center of gravity, means at the midpoint of 5 Newton. That distance from that origin is 0.4 meter. Then we can take our moment about this one. Okay, make it simple. That's our reference point, 2 Newton. Taking about the moment about 2 Newton. Okay, so we take mass times distance. Right? 3 times 0.2, 5 times 0.4, and then 5 times 0.8. Okay, here. And total mass, total weight, we just add all the weight up together. Right? 2, 3, 5 plus 5, 2, 3, 5 plus 5, and then we get our answer, 0.44 meter. How about slightly more complicated, a rectangular piece of plywood measuring 2 meter by 0.8 meter. Okay, this is 0.8, this is 2 meter. Okay, that's 1 meter, that's 1 meter. They give you an origin there. So mass of plate is proportional to the area. Right? Greater area, greater mass. Center of gravity, we divide into A, B, C, D. Take this part there. Right? Center of gravity, right, is halfway. This is 1, this is minus 0.5. Y is 0. Right? The Y coordinate is 0. Center of gravity is here. And then instead of thinking of it as area, we can call the area the mass. Right? So it's 0.8. So this is 1. Right? That 1. This one is 0.8. So 0.8 times 1 is 0.8. So we call that area the mass acting at C. And we look at B, P, Q, C. Right? Center of gravity is at G here. So whether you have a rectangle there, empty rectangle there or not, it's still the same. The center of gravity will be halfway instead of 1. Half of 1 is 0.5. Y is still the same, 0 here. Right? So instead of thinking of all this plate, we can think of the mass as concentrated at G. And this mass concentrated at C. And we just apply the formula. Okay, calculate the area. Right? Since it doesn't tell us, we can roughly estimate. Right? They are even. This is double, this side there, and this side there. These two sides are the same. Right? So this area is 0.8. This area, 1 times 0.8 minus your that area. Right? Is 0.4. This is half. Right? 0.5. So we get 0.6. Okay, y is the same. No need to calculate y. Calculate the center of gravity for x. Right? Using the formula. Okay, there's 0.8 times your x. Right? Negative sign must be there. And 0.6. That's 0.6 times your, right? That's your x. 0.5. Total mass or total area, 0.6 plus 0.8. Calculate out. Minus, that means it to be somewhere here. Near the origin there. Right? It's positive will be here. Negative will be here. Equilibrium of particles. Right? Newton's first law. Newton's first law of motion. A body continues in state of rest or uniform velocity, provided there is no resultant force acting on it. Right? By right, it should be particle rather than body, because where the force act, you will find later on will affect whether it will go moving with constant velocity or whether it will topple over. Right? But we are interested no resultant force act on the body. Newton's first law of motion tells us that for a body to be in equilibrium, the resultant forces is 0 or they balance. There may be forces acting, they balance out. The body is either stationary, that means not moving, or moving at constant velocity, that means moving at constant speed in a straight line. Example of such body, a body moving at terminal velocity in viscous fluid. Okay? Not in air, but in oil. You drop a ball bearing, in oil or glycerin, forces acting will be the way. This is the drag or frictional force from the fluid, from the glycerin. So the forces balance. That's what it means, the balance. The upward force equals the downward force. So you will continue to move with terminal velocity. Or this two-person pulling. Two-person pulling, no resultant force. Forces acting at that point P. F1 is balanced by F2. So they are not, that point P is stationary. No motion. Right? The point P remains stationary. Forces to the right, F1, because forces to the left, F2. Right? Let's review our vectors that we have learned in topic 1, chapter 1. When we study vectors, forces F and S, that's our force F, that's our force S. Right? To find the resultant, we complete our rectangle or parallelogram, and then we place the two force with the diagonal. That's the resultant force, R. Right? Resultant, instead of these two force, we replace it with R. In this topic, we are not interested in resultant force by equilibrium. Okay? Equilibrium, that's the force for equilibrium. So it's the same equilibrium, it's just the same. Right? Instead of resultant force, it's the same magnitude, but opposite direction to the resultant force. Right? Both R and E are equal but opposite direction. Or another way of saying, the forces form a closed triangle. Right? Taken in order, easier to take F and S, then it should form a closed triangle. Or we can use component method. Right? Two forces, can use parallelogram rule as we have done that before. Complete the parallelogram and find the resultant. Or replace each force by component. We replace each vector. This is a vector. Form our square or rectangle. Then replace it with its component. Same with the red force, red vector. Replace it with its component and then remove it. Then we can add all the components in the same direction. Right? In this case, x is 2 plus 5 is 7. Right? And this one is larger, 3. This is 2. So there's a resultant going down. Y is going downwards there. And then this is 7. And we can complete the rectangle and find the resultant. Okay, this is just emphasize the same thing, that's all. Right, the resultant of the component. Okay, let's do an example. A mass held by two wires. Wire 1, wire 2. Right, that's your point P. That's your mass. 40 kilogram. All the forces act at the point P. Right? So tension is always pulling it up. Right? We are looking at the forces acting at P. So tension is pulling it up. We can call that T1. And then T2 is pulling it up again, pulling at point P, pulling it up. We can call it T2. Right? And then the weight act vertically downwards there. 3 coplanar forces in equilibrium, their line of action pass through a point, concurrent. That means all these 3 forces, they are in the same surface or same plane. Right? That's called coplanar forces. So if the line of action or the forces must pass through a point, or we call it concurrent. Coplane means same plane, same surface. In this case, P is a point. Right? Vector equation, we can write a vector equation, easier to take. This is clear. Right? This one we have to roughly estimate. So we write W first, and then after T1 or T2, it doesn't matter, any order. T2, T1, if you write this as a vector equation, it must form a closed triangle. So that's your W. That's your T2, this one, and T1, form a closed triangle. Right? Or you can draw on the diagram itself. Okay? This is your T2, that's your T1. Right? But it must be vertical, this one. Right? So it must be down, coming down. That's your weight. Right? They sometimes ask you magnitude, order of magnitude, then it's better to draw on a diagram. Then you can see which is larger. Right? So summarize, we say that forces are concurrent if they are in equilibrium. Three forces in equilibrium, line of action of forces must pass through a common point. That's what it means by concurrent. Right? Drawbridge, you can find in many places there. Okay? There's a window there. Or people may have crazy idea. They don't want people to know their house, so they may have a tunnel there, a trapdoor there. They meet a friend somewhere, right? Or in the historical time, when they are at war, the soldiers can enter, then the drawbridge can be closed. The enemy cannot enter, right? Because there's water there. Right? Prevent the enemy from entering. So let's look at an example of trapdoor. Right? You want to show all the three forces there, and then give the order of magnitude. Right? First thing, center of this trapdoor is here. That's your center of gravity, C. That's where the weight will act. That's the first one. Weight of the trapdoor. And I remember we are looking at the forces on this trapdoor. Is by the cable, right? Tension by the cable, T. So to find the third force at the pivot, we produce this backwards. Remember that we say that the three forces, their line of action pass through a point. Right? So that is the point. This reaction must pass through this point. So that is your R. Right? Vector equation, W plus T plus R equals to 0. Right? You can do your vector triangle, W. Right? Important, you want order of magnitude. You must draw as close as possible to the magnitude given in the diagram. Right? Direction. Weight is downwards there. Right? That's your T. That's our vector equation. W then T. And must be parallel coming to here. That's your R. So it's very difficult to see from here, but maybe R looks a bit bigger. Right? R, W, T. T is the smallest. Or we can draw on the diagram itself. That's your weight. There's the tension in the cable. Right? The last force, the weight must come, line of action pass through here. Okay, with the cable, there's a point where R will pass through. The line of action of T and the weight, and R will pass through this point. Okay. Right. So it's better to draw on the diagram. Experiment in laboratory, then we can have state forces of equilibrium, right? Either this way or that. Then you can change the weight, change the tension in the string, right? Change the weight, change the tension in the string. A small ring there, a tiny ring. We can change this angle also. And then we can study the three this line produced must meet at the center here. Or we can have pulley here, and then that weight there will provide this tension there. This way will provide the tension. That weight will provide this tension. Okay, so there are various ways to investigate in laboratory. Okay, let's look at some simple example. Diagram shows a bird in flight. In which direction does the weight of the bird act? Right? Must be able to know the weight is vertical downwards on the center of gravity. So answer is donkey. Okay, same thing. Aeroplane is in equilibrium. The diagram shows the forces acting on the aeroplane. Right? You got the lift force from the winds. That's the weight. That's air resistance or we call drag. There's a force from the engine. Which statement about the forces is correct? Remember, it's moving with constant speed, constant height. Force from engine equal to air resistance. Force from engine is air resistance. That's correct. Lift from the wing equals to weight. Right? Our answer is A. Right? Vector diagram, you should be able to say you got a body is acted by two forces, P, Q, and frictional force holds a body in equilibrium. Which vector triangle will represent the relationship between the forces? Right? Should be able to read. Right? In this diagram, this is the resultant. Right? This is the resultant. Right? Key to remember in this answer this question is the three forces must pass through a point or form a closed triangle. So the arrow must always point all clockwise or all anti-clockwise. So A cannot be the answer. That's the resultant. B cannot be the answer because that is the resultant. This one can be because it's all anti-clockwise, form a closed triangle. Okay. This one cannot be because this is the resultant. The answer is C. Okay. Need to know how to draw the forces. A pendulum. There's a pendulum. Of mass 60 grams. It's attached to a string. There's a string. Show the forces acting on the bob. Right? The weight. The first thing is the weight. Act from the center of gravity, pulling it down. And tension will pull on the bob upwards there. P. What's the size of the weight? You must be able to calculate. mg. Right? Mass change to kilogram. Times 9.81. 0.59. Right? How are the forces acting? Forces upward equals forces downwards. Okay. Tension equals to weight. So the two must have the same magnitude. 0.59 Newton. Does the two forces pass through a point? Yeah, the line of action pass through a point. So what can we expect? The resultant force is 0. The particle is, in this case, not moving, stationary. If it's moving, it will move with uniform velocity. Okay, let's try another example. Question 5. Pendulum bob is held stationary by a horizontal force. That's a horizontal force. Three forces acting on the bob are shown in the diagram. Tension in the string is T. It's a tension. The weight of the pendulum is W. Which statement is correct? Okay, as I say, you can use triangle of forces or resolve component. Resolving vertically, replacing P with its component. Right? There's 30 alternate angle. These are parallel line. So it will be T cos 30 equals to W. And resolving horizontally, H equals to T sine 30. Then we can look at the answer. Okay. Is there any answer here? T cos 30 equals, that one is wrong. That one is wrong. W equals to T cos 30. Yeah. Answer is C. Right? Or sometimes they may want to ask you for this one. Then you take 2 divided by 1. Tangent 30 is H over W. Right? Answer is C. Okay, we can use triangle of forces, draw H, and draw W, draw your T. Then there's 30. Okay, now examiner may require you tangent 30 is H over W. So H over W. Okay, A level tend to be easier lah. STPM, they may twist the question around because it's based on mathematics. Need to know inclined plane, rough plane. Rough plane means presence of friction. Right? You're required to show all these forces at normal reaction, weight, friction, and then what will be the friction and normal reaction, and if the block is on the point of sliding, not moving, on the point of sliding, right? You need to know how to calculate the weight. The mass is given. This is usually called friction compensated check. That means the friction is compensated by the component of the weight down the plane. So there's center of gravity, the weight is mg. Right? There's a mass, change it to kilogram times 9.81, and I use 10 or A level or STPM 4.32. So that's your weight. And then this angle 30 is equal to that angle 30. Remember that. And there's a normal reaction. These are the three forces. And then since it's going to slide down, the friction must oppose the motion. They must go up between the two surfaces. So friction equals to your, right? This is 30. That's your friction must be compensated or equals to the weight sine 30. Far away from this angle is W sine 30. And normal reaction must be equals to this component of the weight perpendicular to the plane, W cos 30. Okay, or replace the weight with the component. No? There's a N, there's a W sine 30, there's a W cos 30. Okay, same thing. Right, can try this one. Right? Yeah, very kind. They draw for you all the direction of the forces, but you're required to know direction of the forces at the ring there. What do you observe about three forces in equilibrium? Right? Line of action, pass through a point. That's your point. Yeah, between T1 and T2. First, calculate your weight. Right? 8 kilograms is the mass times acceleration. Use calculator, 28.9. Right? Resolve into component or use triangle of forces. There's your weight. There's your T2. There's your T1. The angle is 30. This is also 30. So cos 30. Cos 30 is W over T1. There's your W. Right? And from there, you can take the T1 there, cos 30 down, calculate out. And tangent 30, T2 over W. Right? T2, W, that's your W. Right? Cross multiply. Using calculator, get the answer. Right? Or sometimes examiner may want to test you whether you understand or not. The three forces in equilibrium must pass through a point, or we say concurrent. The hinge door is held closed in a horizontal position by a cable. There's your cable. There's a hinge. Three forces act on the door. The weight, the forces, tension. The force H at the hinge. Okay, which least give the forces increasing in order of magnitude. So if they want order of magnitude, the size of the three forces, the smaller from smaller to the larger, then it's better to draw in the diagram. Okay? Produce the forces, draw the diagram, produce the line of action. So it's going to be here. That's where it pass through. So the three forces will pass through a point. So that's your weight. That's where the point will pass through. That's your W. That's your H, sorry. Then we can see which one is larger. Smallest one is the weight. And the next one is H. T is the longest. Okay. So you want to list the forces in increasing order of magnitude. Okay. So this is in decreasing order. You want increasing order. W is the smallest and H T is the longest. Choose the correct answer. When three non-parallel forces acting on a body are in equilibrium, the line of action must pass through a point A. Right? Should be able to identify for a cube. Right? If you take this one corner as the origin, then center of gravity is halfway there. Right? 10 cm. Y is 10 cm. Half of that y cm is 5 cm. Half of z-axis is 15. So you should be able to write x, y, z 10, 5, 15 coordinate. Equivalent of rigid bodies. Right? In physics, a rigid body, also known as a rigid object, is a solid body. It is solid body in which deformation is zero. It doesn't increase in length or breadth, or if it does increase, it's so small that it's negligible. Right? Distance between two given points on a rigid body remains constant in time regardless of external force acting on it. Means we don't bother about the extension of the body become longer or shorter, we are not bothered. Right? That's a rigid body. Okay, so for uniform circular motion, right, first law, we can modify it. Uniform circular motion means it's moving in a circular path with constant speed. Not velocity, speed. So object at rest, that's the Newton's first law of motion, remain at rest. An object in motion, continue in motion with the same speed and in the same direction unless acted on by an unbalanced force. Right? Instead of same straight line, we call circular path now. Right? Instead of unbalanced force, there must be a moment or torque. So a body can still be stationary or move with constant speed in a circle or circular path if there's there's no torque. Okay? There's no torque. Okay, so a body move in uniform circular motion because there's a resultant force called centripetal force acts on it, act on the body. That's what we study in chapter 5, uniform circular motion. Okay? These are things that come out in A level in the experiment 201 November. Determine the center of gravity. G is the center of gravity. Right? You swing the card, displace the card will swing until G is below that vertical line. This compound pendulum, right? You can swing you can displace the rod towards you or away from you, and then it will start swinging. We call it compound pendulum because it's the swinging of a body. Right? And this is a pivot, the pin, right? Swing about that point there. That's the pin there. Okay, just review what we have learned just earlier. Where stationary, the line of action of the normal reaction and the weight will pass through the same point. Right? Center of gravity. That's the line of action, the green line. Okay, no perpendicular distance, no moment. Line of action of N, right? Line of action, normal reaction, and W pass through the same point C or coincide. And the center of gravity is just below pivot. W equals to N. When we displace the ruler, small displacement from the rest position. Right? Rest position is where it's not moving here. Right? There's a line of action of W now. Line of action of N is now here. Right? N and W is still equal, but it's now more in equilibrium. Right? There's what we call a clockwise moment. That means it will swing downwards there, clockwise to the rest position. So the displaced ruler will swing and finally return to the rest position. Right? In this case, we're moving down clockwise. That's a perpendicular distance of this weight from the rest position, from the pivot. Right? And then we call the clockwise moment W times R. Right? That's a moment, or that's a torque that causes it to swing. Okay, swing. Swing means there's a resultant moment. Turning effect of force. For no translation, no linear motion, when there is no resultant force acting on the body will stay at rest, provided the force passes through a point. Okay. Three forces acting on the body, that is stationary. The forces to produce a line action will pass through a point. What happens when the forces act on the body does not pass through a common point? Right? The body rotates to a new equilibrium. This turning effect affects the equilibrium of the body. Right? Turning effect of the force. Right? Just like you place a wooden block on a table. Right? It's in equilibrium. Stationary. So the upward force, normal reaction, equals to weight downwards. Right? Friction, if you are applying a force there, apply force, then there is your friction. The two are balanced if it's not moving. If the apply force is greater, then it will accelerate. Okay, that's provided you don't put the force too high. Okay. But the force can cause also rotation. Same wooden block on a table, but right, a force can cause rotation about a turning point. Turning point is your pivot. So instead of applying a force at here, at the center of gravity there, we apply it further up. Then we can see that now there's a pivot there, a turning point. It will rotate, or it will turn about the pivot there, and then it will topple over. So we say that there is now a resultant moment or a torque, means a force acting at a perpendicular distance away that will cause it to topple over. Right? Wooden block topples as a force, has a turning effect about the pivot there. Okay? Vector or cross product. Right? Usually we put our right hand that way, facing A. Important the order of the vector. So we put our right hand facing A, right? Along A and facing B. Along A, facing B, and then the fingers can rotate to B. That's what I mean. And then the thumb will represent direction of C. Right? Vector multiplied by vector is a vector. It's called a vector product. Direction of resultant vector is given by the right-hand grid rule. Right? The magnitude is the area of this parallelogram. This is A, this is B. So that area is the magnitude of C. Right here. Clockwise, so anti-clockwise, torque is up, downwards. If it's going the other way, clockwise, then the torque is downwards. Right? So torque, some group will call moment of the force. Torque is defined as a vector product of position vector. R is the position vector Right? That's the origin, the pivot. And then F is the force. There's the force. Right? R cross F. Important. R comes first times cross F. And all these are vectors. Magnitude is FR sine alpha. Right? Sine alpha doesn't have a unit. Unit is R is meter. F is Newton. Newton meter. Right? So a torque causes a particle to move clockwise or anti-clockwise. This is clockwise. This is anti-clockwise. Okay, so let's define a torque or moment of force. Moment about a point. That's your point. Is force and perpendicular distance from the line of action of the force. So moment of force, or we call torque. There are 4 things you need to remember. A point, where we take the moment about P, right? The force itself, right? Which is the weight of Garfield. Line of action of force, right? You can produce it. That's the line of action, right? Parallel to the weight. And perpendicular distance, that's a line of action. Perpendicular distance, that's a perpendicular distance D. Perpendicular distance D. So it's F times D, force times perpendicular distance. What happens if it's at an angle? You put a door there, that's your force. Put the other hand, you look at the top there, at this angle there, that's the angle theta. That's the length of the door or lever arm. Call it lever arm. That's your pivot, turning point, the hinge. Okay. Lever arm. There's a line, there's your theta. Right? Vertically opposite. This is the line of action of this force F. Line of action. That's a perpendicular distance. Force. Line of action of force and perpendicular distance. Okay, so this is further away from the angle, so it becomes L sine theta. This will be L cos theta. So moment of force times perpendicular distance, L sine theta. Or we can rewrite it as your F associated with sine theta times L. That means rather than go and do all this drawing, we take our L times the component perpendicular to this lever arm, which is your F sine theta. Easier. This is just to show you how X and L are related. This is a perpendicular distance. So sine theta is X over L. Okay, so moment of force about P. Right? Remember, we can replace that force there with a component F sine theta, F cos theta. Okay? This cause stretching. It doesn't cause any rotation. You just call it the rod become longer or pull on the pivot. Right? Pull on the lever arm. So we take perpendicular distance F sine theta times the length. Right? The moment of force is called a torque. So F cos theta, no moment, it doesn't cause a rotation, it causes it to be shorter or longer. That's all. In this case, it's stretching the body. Right? So moments in physics have nothing to do with time. Right? Like English will say in moments like this, meaning time. Moment of force is the turning effect that the force has. It's measured in Newton meter. Right? From the equation. Cannot call it Joule because it's not done. Okay, force and perpendicular distance, you can see some uses. So the moment or torque depend on 2 factors: the size of the force, how big or how small, and the perpendicular distance D. Right? So if there's a constant moment, we can make this force small by making the length D large. same moment. Right? In this case, it will cause it to go clockwise. Right? So moment of force will cause it anti-clockwise or clockwise. In this case, it's clockwise. Right? So a small force applied at a large distance will tighten the nut. Right? You try to tighten the nut, it will be difficult. But with the spanner, it's easy. Right? There's application. You need to recognize clockwise, direction of the clock, this way, clockwise. This is anti-clockwise, right? Anti-clockwise. Right? Must be able to take principle of moment. Says that the sum of clockwise moment about any point is equal to the sum of anti-clockwise moment about the same point. Okay? Or short form, sum of clockwise moment, sum of anti-clockwise moment. In the exam, of course, you cannot write this side, you have to write this side. Right? That's the principle of moment of torque. About any point, no resultant torque. Right? For linear motion, the body to be stationary, move with constant velocity, sum of forces outwards equals sum of forces downwards. Right? W equals to T. So for the seesaw to be horizontal, the Garfield there, FD, there's a pivot. Right? In this case, there's a anti-clockwise moment, so Garfield will topple over. Right? It won't stay horizontal. How to stay horizontal? Right? You must have another person or Audi. Right? Audi is thinner, is fatter, so shorter distance. Right? This is further away. So the idea of clockwise moment equals anti-clockwise moment equals, then it will be balanced. Balance means it will stay horizontal. Right? That's your F1, that's your D1, that's your F2, that's your D2. To be balanced means to be horizontal. Okay, so basically you use clockwise moment because anti-clockwise moment. Right? This condition ensure that the seesaw or the plank is horizontal. It doesn't topple over right, topple over left. Right? But there is also at the pivot there, a reaction force. Right? That reaction force is balanced by F1 and F2. Okay? There are uses there. Right? Application, where you pass a current through a meter, there'll be forces turning it copper. Right? Or tighten the nut. Right? Long spanner make life easier. Right? Can opener, long handle, allow a small force or the effort you apply to open the can. Right? Or this one can find in some rural areas. Right? You don't see in town anymore. Where there's your wheel, there's your axle, there's your rope there, and then there's your well, water below there. Instead of you using physically to lift up the water, you need a lot of weight, a lot of force. Right? We use this wheel. Right? We use clockwise moment and anti-clockwise moment. Right? The wheel is bigger radius R2, axle smaller radius R1. So we just apply a small force here and large distance R2. Right? Application start. Right? Without hammer, lifting the nail from the wooden block would be very difficult. In this case, you apply a small force here, long distance, to pull it up. Right? What's a couple? There's a couple. Two equal, these two are equal. Parallel, right? But opposite forces, right? Equal. Opposite forces whose line of action are different. Okay? Line of action is here, line of action is here, they are different. Right? Or turning a wheel of the car. Right? There is a condition for couple. Couple cause rotation about point P. You see that point there. Right? R is the radius of the wheel. D is the diameter of the wheel. Right? F is the force, right? By the hand. One is going up, it's going down. So we define same thing. R, radius of wheel. D is diameter of wheel. Right? There's your force, couple. The force, the two forces parallel, opposite direction, form a couple. Right? Torque, which is clockwise, or we call it moment of a couple. In this case is clockwise. Right? F times R, F times R. Right? Add that up, 2FR. Right? 2R, 2 times R is the diameter, so it's F times D. So a torque causes rotation, while a force causes linear acceleration. Right? This is acceleration in the circular path. That's what it means by rotation. Acceleration in circular path. Okay, so we can either derive it or we can call torque force and perpendicular distance between the forces itself. Right? Like this elementary, calculate out one by one, we can take one force and the perpendicular distance between the force. That's the torque of a couple. Okay, so this case is clockwise, this case is anti-clockwise. So we summarize condition for equilibrium: no resultant force, no resultant torque, sum of clockwise moment about any point equals sum of clockwise moment about the same point. First condition ensures the body does not accelerate, or we call it no translation, no linear motion. Linear motion is with constant speed. Second condition ensure there's no rotation, or we rotate, it rotates with constant speed. It doesn't become faster and faster. Right? What is the magnitude of W? What's the reaction of the pivot? Right? Taking moment about pivot. That's a pivot. Right? Sum of clockwise because sum of anti-clockwise. Right? In the exam, write down. Right? This is my short form. Okay, 300 times 1. And 450 times 1.5 equals to, right? This anti-clockwise W times 1.5. 350 Newton. Reaction force is here. Right? Pivot must push up to balance it so that it doesn't all push down on the pivot. The pivot must push up. The forces outwards there because the forces downwards, sum of forces outwards, sum of forces downwards. Right? So R is upwards, W is down, 300 is down, 450 is down. So W is 750. Add them up, you get R. Okay, so we can summarize it. Right? Center of gravity, know what is center of gravity? What is center of mass? Right? How to calculate center of mass? Equilibrium, no resultant force. Forces taken in order from a closed triangle or polygon. Then action of the three forces pass through a point. Right? Under equilibrium of rigid body, we define torque, right? Or call it moment of force and perpendicular distance. Then we define our principle of moment, right? Sum of clockwise moment equals sum anti-clockwise moment. And condition for equilibrium, no resultant force, no resultant torque at any point. Okay, let's try an example. This one, half meter rule, 50 cm. On a smooth horizontal surface, it's free to rotate about a vertical axis through a hole. Yeah, that's the hole there, 20 cm mark. Forces of equal magnitude, 4 Newton. 4 Newton at the end of the ruler in opposite direction as shown. What's the resultant torque? Right, remember, we want force times perpendicular distance. Take one force times perpendicular distance. So force is, right, take one force, 4 times sine, right? Perpendicular force component, vertical component, 4 sine 30 times the length change it to meter. This 1.0. Answer is B. Okay. A heavy beam of weight W rests on a small sphere with one end on a round floor as shown. Which figure correctly shows the forces acting on the beam? So this one, right, this particular body or plank resting on the sphere. So where it rests, there must be a normal reaction from the surface here, perpendicular to the surface there. So there's your reaction or normal reaction. And then from the floor, there must be a normal reaction upwards there. And because that plank there or heavy beam will move to the left, friction must come to the right. And the weight act at the center of gravity must go downwards there. But we don't see this as a separate force, F and N. We can form a rectangle and then find the resultant. And the best answer is this one, B. Okay, the reaction is here. Meter rule is free. Meter rule is free hinged at O mark and is free to rotate about a horizontal axis about the hinge. The weight of the ruler is 4 Newton and the weight is, they are very kind to you. There's your weight, 2 Newton, fixed at the 80 cm mark as shown in the figure. What's the torque on the meter rule when it makes an angle of 30 degrees? Right? So torque in this case will be clockwise. Right? Is force times your perpendicular distance. Right? Is 0.5. Right? 1 meter rule. There's 50 cm here. So 0.5. Change the cm to meter times your sine 30. And then this is your 2 Newton. Right? Times your 80 cm, change to meter, 0.8, sine 30. Okay, A. A heavy uniform beam of length L supported at P and Q as shown in the diagram. What's the ratio of F1 to F2? Right? We don't know the weight. So let the weight be at center of gravity. Right? The whole length, add these two together is L. So half the length is half L. This is also half L from the center of gravity. Right? And this length there, that distance there, right, is half L, 3/6 L minus your L/3. Right? L/T is 2/6 L. So that distance is L/6. Right? We're not interested in W. W will act at C there. So we take moment about the center of gravity, then we don't have to worry about W. Right? So clockwise, we're anti-clockwise. So clockwise, F times the that distance of L. That's our keyword C. Anti-clockwise is F2 times our L/6. Then take our F2 down. Take this 2 up. Take this L down. Simplify it, we get 1/3. Answer is A. Okay, so we will end the lecture here. Thank you for your time. Okay, so that's our time. Let's end it here.